Alright. Hey, what's going on, everybody? Welcome back into the stream today. Hope you guys are having a good day today. My name is Michael. Welcome back into my stream. Today we're going to be jumping back into our reading today. Should be a good session. Let's get a new directory here. Chapter 3. Alright, let's get into this. Chapter 3. Characterizing running times. Okay. Yo, how's this? Hey, Abdul, how's it going? Welcome back into the stream. I hope you're doing well. Welcome, my friend. He asks, how's this compared to DSA with Python? Honestly, I like this one a little bit better. It's a little bit more generalized for kind of more. It just doesn't require as much niche Python knowledge as the DSA in Python does. That requires quite a bit of Python, like intermediate knowledge, and uses some kind of heavier syntax and pseudocode. So I really enjoy the this book as it kind of is more the goal in the kind of author notes from the MIT staff that wrote this book is that they really wanted to provide a book that really you could pick up at any chapter and and learn that individual section. Like you don't really need each chapter to build on one another, as well as more generalized, rather not so niche and whatnot. But I like it. Thanks for the question, man. Have you read any of these books, or what kind of books do you like to read, Abdul? All right, you guys. Let me go ahead and grab my my light real quick. Hold on, let me grab my light. One second, y'all. Plug in the light. All right. Nice. Let there be light. Sweet. All right. Let's get back in. Let's do a little intro here. All right. Hello, everybody. Oh, hold on. Let me go ahead and fix this chat box. I want to. I think it should be okay. Let me make sure here. Let me just really quickly. Yo. I think it should. I kind of need to spam it here, unfortunately. I want to see if it'll go the full distance of my screen and scroll. Okay, good. All right, nice. Let's go to the social stream. Let's clear all. Okay. And let's go here. Yo. Nice. Abdul says, I've been working on Python's data structures and algorithms on Udemy, but I'm exploring other options on what would be better. Have you found that you don't like it as much, or why you wanted to explore different options? I found that the books are really helpful, honestly. They have all of the information needed, and they're what taught at the college level. So, no. Okay, I got that. I kind of lowered the chat height a little bit, so it wasn't as high. Okay, let's get into this. I'm gonna also make my Twitch alerts um, be a little bit smaller. Over off to this side here. There we go. Cool. All right, let's go ahead and start this recording. All right, everybody, we are jumping back into Introductions to Algorithms by CLRS, or Corman, Laerson, Rivest, and Stein. We're going to jump back into Chapter 3 today. It's going to be awesome. Thanks so much for being here, and make sure if you would like to follow along live as I stream, as I read, you can do so, but I'm chopping this up for a watch along on my channel. So thanks so much for being here, and I'll see you guys in the next one. Let me redo that, actually. That was terrible. Hello, everybody. My name is Michael. Thanks so much for joining me again today. We're going to be jumping back into our reading of Introductions to Algorithms, 4th edition by CLRS, or the MIT staff. This is going to be a great session today, and I'm looking forward to reading Chapter 3. Let's go ahead and get started today. All right. Cool. Let's get into Chapter 3. All right. All right. Let's get into this. Chapter 3. Hey, Chucky, how's it going? Chapter 3. Alright, Chapter 3. Characterizing running times. The order of... Hold on, I have a fan in the background. Probably annoying. The order of growth of running time of an algorithm defined in Chapter 2... Oh, hold on, let me close the door. Oh my gosh. This one down a little bit. Okay. Alright. Chapter 3. Characterizing running times. An order of growth of the running time of an algorithm defined in Chapter 2 gives a simple way to characterize the algorithm's efficiency and also allows us to compare it with alternative algorithms. Once the input size n becomes large enough, merge sort with its n log n worst case running time beats insertion sort, whose worst case is theta n squared. Although we can sometimes determine the exact running time of an algorithm, as we did for insertion sort in Chapter 2, the extra precision is rarely worth the effort of computing it. For large enough inputs, the multiplicative constants and lower order terms of an exact running time are dominated by the effects of the input size itself. When we look at the input size large enough to make relevant only the order of growth of the running time, we are studying the asymptotic efficiency of algorithms. Asymptotic efficiency. Right. Input size large enough to make relevant only the order of growth of the running time. That is, we are concerned with how the running time of an algorithm increases with the size of the input in the limit, as the size of the input increases without bound. Usually, an algorithm is asymptotically more efficient, is the best choice for all but very small inputs. This chapter gives several standard methods for simplifying the asymptotic analysis of algorithms. The next section presents informally the 3 most common used types of asymptotic notation, of which we have already seen an example of in theta notation. It also shows one way to use these asymptotic notations to reason about the worst case running time of insertion sort. Then we will look at asymptotic notations more formally and present several notational conventions used throughout this book. The last section reviews the behavior of functions that commonly arise when analyzing algorithms. O notation, omega notation, and theta notation. I'll have to go back and fix those guys. When we analyzed the worst case running time of an insertion sort in chapter 2, we started with the complicated expression of this. We then discarded the lower order terms and these constants, and we also ignored the coefficients of n squared, right? That just left us with the factor of n squared, which we put into theta notation as theta n squared. We use this style of characterizing running times of algorithms. Discard the lower order terms of the coefficient of the leading term and use a notation that focused on the rate of growth of the running time. Theta notation is not the only such asymptotic notation. In this section, we'll see other forms of asymptotic notation as well. We'll start with intuitive looks at these notations, revisiting insertion sort to see how we can apply them. In the next section, we'll see the formal definitions of our asymptotic notations along with the conventions for using them. Before we get into specifics, bear in mind that the asymptotic notations we'll see are designed so that they characterize functions in general. So it so happens that the functions we are most interested in denote the running times of algorithms, but asymptotic notation can apply to functions that characterize some other aspect of algorithms, the amount of space they use, for example, or even to functions that have nothing whatsoever to do with algorithms. Okay. Okay, O notation, or big O, right? O notation characterizes an upper bound on the asymptotic behavior of a function. In other words, it says that a function grows no faster than a certain rate based on the highest order term. Consider the example, the function 7n cubed plus 100n squared minus 20n plus 6. Its highest order term is 7n cubed, and so we will say that this function's rate of growth is n cubed. Because this function grows no faster than n cubed, we can write it as O of n cubed. You might be surprised that we can also write the function 7n cubed plus 100n squared minus 20n plus 6 is O of n to the fourth. Why? Because the function grows more slowly than n to the fourth, we are correct in also saying that it grows no faster. As you might have guessed, this function is also O of n to the fifth, O of n to the sixth, and so on, and more generally, it is O of n to the c for some constant where c is greater than or equal to 3. Gotcha. Cool. In other words, a function based on the highest order term. Right. Omega notation. Omega notation characterizes a lower bound on the asymptotic behavior of a function. Right? In other words, it says that a function grows at least as fast as a certain rate based, as in O notation, on the highest order term. Because the highest order term in the function 7n cubed plus 100n squared minus 20n plus 6 grows at least as fast as n cubed, right? This function is omega of n cubed. This function is also omega n squared and omega of n. More generally, it is omega of c, or n to the c, for all any constant where c is less than or equal to 3. Right, it goes at least as fast as that. Right, n cubed grows faster than n squared and grows faster than n. And if we grow at least this fast, we are encompass the speeds of these other two as well. All right, and now let's look at theta notation. I have to fix these. Here, let's go here. Let's grab this theta. Here, there we go. Okay. Theta notation characterizes a tight bound on the asymptotic behavior of a function. It says that a function grows precisely at a certain rate, based once again on the highest order term. Right? A function grows precisely at a certain rate, based once again on the highest order term. Okay. And then this is italicized here. Okay. Put another way, theta notation characterizes the rate of growth the function to within the rate of growth of the function to within a constant factor from above and to within a constant factor from below. These two constant factors need not be equal. If you can show that a function is both O of f of n and omega f of n for some function f of n, then you have shown that the function is theta of f of n. The next section states that this fact as a theorem. For example, since the function that we've been looking at, 7n cubed plus 100n squared minus 20n plus 6, is both O of n cubed and omega n cubed, it is also theta of n cubed. Example on insertion sort. Let's revisit insertion sort and see how to work with asymptotic notation to characterize its theta n squared worst case running time without evaluating summations as we did in chapter 2. Here is the insertion sort procedure once again. Right, this is the pseudocode for insertion sort. What we can observe about how the pseudocode operates: the procedure has nested loops. The outer loop is a for loop that runs in n-1 times, right? It runs one shy of the amount of items, regardless of the values being sorted. The inner loop is a while loop, but the number of iterations it makes depends on the values being sorted. The while loop starts at j, and variable j starts at I less than 1, right? And decreases by 1 in each iteration until it either reaches 0 or a index of j, right, the value that we're currently looking on, is less than or equal to the key. For a given value of I, the while loop might iterate 0 times or all the way up to I minus 1 times, or anywhere in between. So the body of the while loop, lines 6 through 7, takes constant time per iteration of the while loop. These observations suffice to deduce an O of n squared running time for any case of insertion sort, giving us a blanket statement that covers all inputs. The running time is dominated by the inner loop, because each of the n-1 iterations of the outer loop causes the inner loop to iterate at most I-1 times. And because I is at most n, the total number of iterations of the inner loop is at most n-1 times n-1, which is less than n squared. Since each iteration of the inner loop takes constant time, the total time spent in the inner loop is at most constant times n squared, or O of n squared. With a little creativity, we can also see the worst case running time of an insertion sort is omega of n squared. By saying that the worst case running time of an algorithm is omega n squared, we mean that for every input size n, right, above a certain threshold, there is at least one input size of n for which the algorithm takes at least c some constant times n squared time for some positive constant c. It does not necessarily mean the algorithm takes at least c of n squared time for all inputs, but there is at least one input within some size n that does take that time. Right? Let's now see the worst case running time for insertion sort is omega n squared. For a value to end up to the right of where it started, it must have been moved into line 6. In fact, for a value to end up k positions to the right of where it started, line 6 must have been executed k times, and line 6 is this increase of the current j position to the right on that inner loop as we move for the insertion sort portion. In fact, for a value to end up k positions to the right of where it started, line 6 must have executed k times. As figure 3.1 shows, let's assume that n is a multiple of 3 so that we can divide the array A into groups of n divided by 3 positions. Suppose that in the input to insertion sort, the n over 3 largest values occupy the first n over 3 array positions, so the first third of the array. This does not matter what relative order they have within the first third of the positions. Once the array has been sorted, each of these third of the values ends up somewhere in the last third of the positions. For that to happen, each of these, n divided by 3 values must pass through each of the middle positions. Each of these n divided by 3 positions must pass through these middle positions, one position at a time, by at least n divided by 3 executions in line 6. Because at least n over 3 values have to pass through at least n over 3 positions, the time taken by an insertion sort in the worst case is at least proportional to that same kind of thing we saw before, of this n squared kind of dynamic, n squared over 9, where we drop the constant, which is omega n squared. Because we have shown the insertion sort runs in O of n squared in all cases that there is an input that makes it omega n squared time, we can conclude that the worst case running time for insertion sort is theta n squared. It does not matter that the constant factors for upper and lower bounds might differ. What matters is that we have characterized the worst case running time to factor constant factors. What matters is that we have characterized the worst case running time to within constant factors, discounting lower order terms. This argument does not show the insertion sort runs in theta n squared time in all cases. Indeed, we saw in chapter 2 the best case is theta n, right, where they're all sorted right off the jump. Now, this is just in the worst case running time, as we saw. Nice. 3.2, asymptotic notations, formal definitions. Okay. Have you seen asymptotic notation informally? Let's get more formal. The notations we use to describe the asymptotic running time in an algorithm are defined in terms of functions whose domains are typically the set n of natural numbers and the set r of real numbers. Such notations are convenient for describing a running time function t of n. This section defines the basic asymptotic notations and also introduces some common proper notational abuses. So I'm going to kind of take this image here. I think this is probably a good one to have in here. Right, so we have f of n is O of g of n because it's bound by that g of n. And the worst case of g of n, and then it's bound in between. Yeah, I like that. O notation. As we saw in section 3.1, O notation describes the asymptotic upper bound. We use O notation to give an upper bound on a function to within a constant factor. Here's the formal definition of O notation. For a given function g of n, we denote by O of g of n, pronounced big O of g of n, or sometimes just O of g of n. The set of functions O of g of n is equal to the set of f of n. There is no positive constant c and not such that 0 is less than or equal to f of n, which is less than or equal to some constant g times g of n. So this is saying that Again, I'm kind of applying those all real numbers, and as we stated above, right? A function f of n belongs to the set O of g of n if there exists a positive constant c such that f of n is less than or equal to c times g of n for sufficiently large n. Right, you're bounded on the upper bound here. You're less than, the function is bound by this upper bound of g of n, right? For some constant c. I think that's what we're interpreting. Figure 3.2a shows the intuition behind O notation, which is this guy here, right? Where you have this some constant c g of n, which is the upper bound for sufficiently large n values of this function f of n. So because f of n is bounded upper above, for n values greater than this n naught, we can see that this is big O of g of n for f of n. Yeah. The definition of O of g of n requires that every function f of n is in the set O of g of n be asymptotically non-negative. F of n must be non-negative whenever n is sufficiently large. An asymptotically positive function is one that is positive for all sufficiently large n. Consequently, the function g of n itself must be asymptotically non-negative, or else the set O of g of n is empty. We therefore assume that every function used within O notation is asymptotically non-negative. This assumption holds for the other asymptotic notations defined in this chapter as well. You might be surprised that we define O notation in terms of sets. Indeed, you might expect that we would write f of n is in, right, I think that's what that means, O of g of n, to indicate that f of n belongs to the set of O of g of n. Instead, we usually write that f of n equals to O of g of n and say that f of n is big O of g of n to express the same notion. Although it may seem confusing at first to abuse equality in this way, we'll see later in this section that doing so has its advantages. Let's explore an example of how to use the formal definition of big O notation to justify our practice of discarding lower order terms and ignoring the constant coefficient of the highest order term. We'll show that this function, right, 4n squared plus 100n plus 500 is equal to O of n squared, even though the lower order terms have much larger coefficients than the leading term, right? We need to find positive constants c and n naught such that 4n squared plus 100n plus 500 is less than or equal to c of n squared, c times n squared, for all n that is greater than or equal to n naught. Dividing both sides by n squared gives us this, right? This inequality is satisfied for many choices of c and n naught. For example, if we choose n naught to equal 1, then this equality holds for c equals to 604. If we choose n naught equals to 0, then the c becomes 19 works. And choosing n naught equals 100 allows us to use a c of equal to 5.05. We can also use the formal definition of O notation to show that the function n cubed minus 100n squared does not belong to the set O of n squared, even though the coefficient n squared is a large negative number. If we had n cubed minus 100n squared is equal to O of n squared, then there would be positive constant c and n naught such that n cubed minus 100n is less than or equal to some constant c times some value squared, times n squared, for all n's that are greater than n naught. Again, we divide both sides by n squared, giving us this reduction, n less than 100 is less than or equal to c. Regardless of what value you choose for the constant c, this equality does not hold for any value of n greater than c plus 100. Interesting. So I kind of want to, let's go ahead and break down this example. Can you break this down in more simple terms? We're talking about big O notation, which is just a way to describe how fast a function grows as n gets very large. The formal definition says that a function f of n is O of g of n if there exists some constant c's that are greater than 0 and some n value, initial starting n value that's greater than 0, such that this inequality is satisfied. F of n, the function, is less than or is bounded on its upper bound by some constant c times g of n for all n values that are greater than or equal to n naught. Let's apply that to the examples. We want to prove this. As n gets really large, the 4n squared term dominates. The smaller terms eventually don't matter in comparison. So we divide everything by n squared, which would give you this. When n is small, the fractions might be big, but as n grows big, these fractions shrink to 0. For large enough n, the inequality is true. Got you. So it's just kind of proving it mathematically. Interesting. Omega notation. Just as O notation. Oop, my stream is dropping frames here. Let's wait a second for something. Okay, we're back. There we go. Oh, we'll let it catch back up here. All right, looks like we're back. Okay, we're back. Okay, omega notation. Just as O notation provides an asymptotic upper bound on function, omega notation provides an asymptotic lower bound. For a function g of n, we denote the omega of g of n, pronounced omega, big omega of g of n, or sometimes just omega of g of n, the set of functions, right? Where omega of g of n is equal to the set of f of n's if there exists a positive constant c and n naught such that 0, which is less than or equal to c times g of n, which is less than or equal to f of n, right? The omega is that lower bound. So f of n would be greater than all constant c and times some g of n, where the n is greater than n naught, some value like sufficiently large. Figure 3.2b shows the intuition behind omega notation. For all values n at or right of the n naught, the value of f of n is on or above this constant times g of n. It's the lower bound. I've already shown that this is equal to O of n squared. Now let's show that this function is omega of n squared. We need to find positive constants c and n naught such that 4 of n squared plus 100n plus 500 is greater than, or has a lower bound, which is greater than or equal to c of n squared for all n greater than or equal to n naught. As before, we divide both sides by n squared, giving us this reduction. This inequality holds when n naught is any positive integer and c is equal to 4. Right? If we had subtracted the lower order terms from the 4n squared instead of adding them, what if we had subtracted instead of added, right? What if we had a small coefficient for the n squared term? The function would still be omega of n squared. For example, let's show that n squared divided by 100 minus 100 and minus 500 is equal to omega squared. If we divide both sides by, I know n squared gives us this reduction. We can choose any value for n naught that is at least this 10,005 and find a positive value for c. For example, when n naught is equal to, this is the minimum n value you can have, where you can have a positive constant. We can choose a constant that is this. It's really small, but it's positive. Yes, it's a tiny value for c, but it is positive. If we select a value or larger value for n naught, we can also increase c. Right, so you're just trying to find the minimum value of a sufficiently large n sample size to where this inequality holds true for that lower and upper bound as described above. So by just kind of isolating the constant, we can find and plug and chug basically n values until c becomes positive. And once that happens, we have found a sufficiently large n value, n naught, and any values greater than there will suffice for that inequality, right? I think that's what we're getting at here. Cool. So it's just showing that you can increase n and get an even larger c value. Just it'll take probably a while. Theta notation. We use theta notation for asymptotically tight bounds. For a given function g of n, we denote theta g of n as the set of functions of, right? this, where we have the function is in between c1 of g of n and some c2 of g of n, right? We're bounded on the both upper and lower, as we stated before. Figure 3.2c shows the intuition behind theta notation. For all values of n at or to the right of n naught, or like no greater, at n naught or greater, the value of f of n lies at or above c1 times gn and below some constant c2 times gn. In other words, for all n values that are greater than n naught, or the first sufficiently large n value, the function f of n is equal to g of n to within constant factors. The definition of omega and theta notations lead to the following theorem, whose proof we will leave as exercise 3.2.4. Theorem 3.1. For any two functions, f of n and g of n, we have f of n is equal to theta of g of n if and only if f of n is O of g of n and f of n is omega of g of n. We typically apply theorem 3.1 to prove asymptotically tight bounds for asymptotically upper and lower bounds. Let's go ahead and take this theorem here. Nice. All right. Asymptotic notation and running times. When you use an asymptotic notation to characterize an algorithm's running time, make sure that the asymptotic notation you use is precise as possible without overstating which running time it applies to. Here are some examples of using asymptotic notation properly and improperly to characterize running times. Let's start with insertion sort. We can correctly say that insertion sort's worst case running time is O of n squared, omega n squared, and due to theorem 3.1, theta n squared. Although all three ways to characterize the worst case running time are correct, the theta n squared bound is the most precise and hence the most preferred. We can also say that the insertion sort's best case running time is O of n, omega n, and theta n, again with the theta n the most precise and therefore most preferred. Here is what we cannot correctly say. Insertion sort's running time is theta n squared. That is an overstatement because by omitting worst case from the statement, we're left with a blanket statement covering all cases. The error here is that insertion sort does not run in theta n squared time in all cases as we've seen. It runs in O of theta n time in the best case. We can correctly say that insertion sort's running time is O of n squared, however, because in all cases its running time grows no faster than n squared. When we say O of n squared instead of theta n squared, there is no problem in having the case which running time grows more slowly than n squared. Likewise, we cannot correctly say that insertion sort's running time is theta n, but we can say that its running time is omega n, right? How about merge sort? Since merge sort runs in theta log n log n time in all cases, we can just say that the running time is theta n log n without specifying worst case, best case, or any other case. People occasionally conflate O notation with theta notation by mistakenly using O notation to indicate an asymptotically tight bound. No, O notation is upper bound, right? So the precision of it's only theta notation is equal to O notation if omega notation is also equal to O notation. They say things like an O of n log n running time algorithm runs faster than an O of n squared running time algorithm. Maybe it does, maybe it doesn't. Since O notation denotes only an asymptotic upper bound, that so-called O of n squared time algorithm may actually run in O of n time, right? It's just like kind of talking about statistical like odds or whatever, right? There are certain inputs to n where you will hit that upper bound, but in some instances, in some cases, right, where you have an array that's already sorted or an array that's partially sorted, you won't really hit that bound as heavily, or you won't even hit it at all. You could run in linear time with a completely already sorted array, or if your array is partially sorted, like I said, your weight or your impact to that upper bound isn't as drastic as, let's say, an array that's completely random. There's no sorting at all into it. So that's kind of what it's getting at here. We typically use asymptotic notation to provide the simplest and most precise bounds possible. For example, if an algorithm has a running time of 3n squared plus 20n, in all cases we use asymptotic notation to write that its algorithm is theta n squared. Strictly speaking, we are also correct in writing that the running time is O of n cubed, or theta n squared plus 20n. Neither of these expressions is as useful as writing theta n squared. In this case, however, O of n cubed is less precise than theta n squared if the running time is 3n squared plus 20n, and theta n squared plus 20n introduces complexity that obscures the order of growth. By writing the simplest and most precise bounds, such as theta n squared, we can categorize and compare different algorithms. Throughout the book, you will see asymptotic running times that are always based on the polynomials and logarithms functions, such as n log squared, n log base 2n, n squared log n, or n to the power of 1/2. Is this log squared or is this base? This might be log squared. You will also see some other functions such as exponentials, log n, and log star n. Interesting. See section 3.3. It is usually fairly easy to compare the rates of growth of these functions. Problem 3.3 gives you good practice. Interesting. Asymptotic notations in equations and inequalities. Although we formally define asymptotic notation in terms of sets, we use the equal sign instead of the set membership of within, is in, or within formulas. For example, we wrote that 4n squared plus 100n plus 500 equals to O of n squared. We might also write 2n squared plus 3n plus 1 equals to 2n squared plus theta n. How do we interpret such formulas? When the asymptotic notation stands alone, that is, not within a larger formula, on the right-hand side of an equation or inequality, as in this, right? The equal sign means set membership. 4n squared plus 100n plus 500 is in O of n squared. In general, however, when asymptotic notation appears in a formula, we interpret it as a standing for some anonymous function that we do not care to name. For example, in this formula where you can see we have the notation within a function, it means that 2 of n squared plus 3n plus 1 is equal to 2n squared plus f of n, where f of n is in, theta n. In this case, we let f of n equal to 3n plus 1, which indeed belongs to theta n, right? It's just kind of abstracting some function that you don't really care about, the actual, orders of the coefficients. You can just kind of, make a variable for the actual notation, kind of. Using asymptotic notation in this manner can help eliminate inessential detail and clutter in an equation. For example, in Chapter 2, we express the worst-case running time of merge sort as this, where t of n is equal to 2t n divided by 2 plus theta n. If we are only interested in the asymptotic behavior of t of n, there is no point in specifying all the lower order terms exactly, because they are all understood to be included in the anonymous function denoted by the term theta n, right? The number of anonymous functions in an expression is understood to be equal to the number of times the asymptotic notation appears. For example, in this expression, sum of I equals to 1 for some value of n, all the values are O of I. There's only a single anonymous function, a function of I. This expression is thus not the same as O of 1 plus O of 2 all the way up to O of n, which doesn't really have a clean interpretation. In some cases, asymptotic notation appears on the left-hand side of an equation as in this. Interpret such equations using the following rule. No matter how the anonymous functions are chosen on the left of an equal sign, there's always a way to choose an anonymous function on the right of the equal sign to make the equation valid. Thus, our equation means that for any function f of n within theta of n, there is some function g of n that is within theta of n squared. Got you. So with any, interest, so it's equal, so it's kind of nested within this, such that 2 of n squared plus f of n is equal to g of n for all n. In other words, the right-hand side of an equation provides a coarser level of detail than the left-hand side. We can chain together a number of such relationships as in this. where we have 2n squared plus 3n plus 1 is equal to 2n squared plus theta n equals to theta n squared. By the rules above, interpret each equation separately. The first equation says that there is some function, f of n, that is within theta n, such that n squared, 2n squared plus 3n plus 1 is equal to 2n squared plus f of n for all n. Right, just this first part. The second equation says that for any function g of n, right, just the next function, right, f, g, within the set of g of theta n, such that as f of n, as mentioned, there is some function h of n that is within n squared, this here, right? So it's kind of saying that this entire function is h of n, I believe, right? Whereas this is like g of n. Besides the abuse of equality to mean set membership, which we now see as a precise mathematical interpretation, another abuse of asymptotic notation occurs when the variable tending toward infinity must be inferred from context. For example, we say that O of g of n, when we say O of g of n, we can assume that we're interested in the growth of g of n as n grows. And if we say O of g of n, or g of m, sorry, we're talking about the growth of g of m as m grows. The free variable in the expression indicates that the variable is growing to infinity. The most common situation requiring contextual knowledge of which variable tends to infinity occurs when the function inside the asymptotic notation is a constant, as in the expression O of 1. We cannot infer from the expression which variable is going to infinity because no variable appears there. The context must disambiguate. For example, if the equation using asymptotic notation is f of n equal to O of 1, it's apparent that the variable we're interested in is it is apparent the variable we're interested in is n. Knowing from context that the variable of interest is n, however, allows us to make perfect sense of the expression by using the formal definition of O notation. The expression f of n equals to O of 1 means that the function f of n is bounded from above by a constant n that goes to infinity. Technically, it might be less ambiguous if we explicitly indicate the variable tending to infinity in the asymptotic notation itself, but that would clutter the notation. Instead, we simply ensure that the context makes it clear which variable or variables tend to infinity. When the function inside the asymptotic notation is bounded by a positive constant, as in t of n equals to O of 1, we often abuse asymptotic notation in yet another way, especially when stating recurrences. We may write something like t of n equals to O of 1 for n less than 3. According to the formal definition of O notation, this statement is meaningless because the definition only says that t of n is bounded by a positive constant, c, for all n values that are greater than or equal to n naught, for some n naught greater than 0. For the value t of n for n less than n naught need not be so bounded. Thus, in the example t of n equals to O of 1 for n less than 3, we cannot infer any constraint on t of n when n is less than 3, because it might not be that n naught is greater than 3. Interesting. What is conventionally meant when we say t of n is equal to O of 1 for n less than 3 is that there exists a positive constant c such that t of n less than that constant for t of n is less than that constant for n's that are less than 3. This convention saves us the trouble of naming the bounding constant, allowing us to remain anonymous while we focus on more important variables in analysis. Hey Ray, how's it going? Hey Tim, welcome back in, dude. Touching grass this weekend was good. We're back though. Similar abuses occur when they with the other asymptotic notations. For example, t of n is equal to theta of 1 for n less than 3 means that the function t of n is bounded above and below by constants by causative constants when n is less than 3. Occasionally, the function describing an algorithm's running time may not be defined for certain input sizes. For example, when an algorithm assumes that the input size is an exact power of 2, we still use asymptotic notation to describe the growth of the running time, understanding that any constant constraints apply only when the function is defined. For example, suppose that f of n is defined only on a subset of the natural or non-negative real numbers. Then f of n equals to O of g of n means that the bound 0, which is less than or equal to t of n, which is less than or equal to some constant times g of n, in the definition of O notation holds for all values that are greater than that initial n naught, or equal to, right, over the domain of f of n, that is, where f of n is defined. This abuse is rarely pointed out since what is meant is generally clear from context. In mathematics, it's okay and often desirable to abuse a notation as long as we don't misuse it. If we understand precisely what is meant by the abuse and don't draw incorrect conclusions, we can simplify our mathematical language, contribute to our higher level understanding, and help us focus on what really matters. Okay, I'm going to copy this, and I'm going to say, can you break this down? Attempting to reconnect. No. Which variable is growing? Normally, when we write O of g of n, it is clear that n is approaching infinity. As we wrote O of g of m, it is about m is approaching infinity. The variable inside tells us which one is getting large. If we write O of 1, there is no variable in sight. Does n grow? M? Something else? You have to use some context. For example, if you see f of n is equal to O of 1, I got you Innovatech. If you see f of n is equal to O of 1, it means that as n grows, f of n stays bounded by some constant. When we say t of n is equal to O of 1 for n less than 3, it's technically nonsense under the strict definition. Formally, right, we know that we have these bounds over our n, but they're applying it to small values. So strictly speaking, it doesn't really mean anything. For n is less than 3, the value of t of n is bounded by some constant. It's just shorthand to avoid writing something clunky like this, when the function isn't defined everywhere. Okay, interesting. Couple more pages, we're almost done, I think. O notation. The asymptotic upper bound provided by O notation may or may not be asymptotically tight. The bound 2n squared or 2n squared equals to O of n squared is asymptotically tight, but the bound 2n squared equals to O of n squared, or 2 of n equal to O of n squared, is not. We use O notation to denote an upper bound that is not asymptotically tight. We formally define little o of g of n as the set. Okay, interesting. I've never heard this. So we use little o notation for any positive constant. There exists a constant n naught greater than 0, such that 0 is greater than f of n. For example, 2n is equal to little o of n squared, but 2n squared does not equal to O of n squared. The definitions of O notation and little o notation are similar. The main difference is that in f of n equals to big O of g of n, the bound 0, which is less than f of n, which is less than or equal to some, the bound g of n, holds for some constant c greater than 0. But in f of n of little o of g of n, the bound O, or 0, is less than or equal to f of n, which is less than c of g of n, holds for all constants c of 0, c greater than 0. Intuitively, in little o notation, the function f of n becomes insignificant relative to g of n as n gets large. Some authors use this limit as the definition of the o notation, but the definition in this book also restricts anonymous functions. Omega is to, by analogy, little omega notation is to big omega notation as little o notation is to o notation. We use little omega notation to denote a lower bound that is not asymptotically tight. One way to define it is where f of n is within some set omega of g of n, if and only if the g of n is within little o of fn. Formally, however, we define little omega of g of n as the set little omega g of n equals to the set f of n for any positive constant c of 0, c greater than 0. There exists a constant n value that's greater than 0, such that 0 is less than c of g of n, which is less than f of n. Where the definition of little o notation says that f of n is less than c of g of n, p times g of n, the definition of little omega notation says the opposite, that c times g of n is less than f of n. For examples of little omega notation, we have n squared divided by 2 equals to little omega of n. But n squared divided by 2 does not equal to little omega of n. The relation of f of n equals to little omega of n g of n implies that the limit as n approaches infinity of f of n over g of n is equal to infinity. If the limit exists, that is, f of n becomes arbitrarily large relative to g of n as n gets large. What in the world? Big O says that f of n grows no faster than some multiple of g of n. Little o says that f of n grows strictly slower. Formally means that some constant is not big enough. In little o, f of n becomes insignificant to g of n. Break it down in simple terms. So big O versus little o grows at most like g of n. Could grow slower, could grow at the same speed. Little o grows strictly slower, never grows as fast. Oh, okay. So by having this not, it's always less than the bound, it's not ever equal to the bound. Okay, I got you. So we'll say little o notation. We'll say omega, little omega notation here. I need to figure out, I'll have to come back and do these, right? So, okay, I get it. Okay, interesting. Comparing functions. Many of the relational properties of real numbers apply to asymptotic comparisons as well. For the following, assume that f of n and g of n are asymptotically positive. F of n equals to theta of g of n and g of n equals to theta of f of n, h of n imply that, what is going on? Okay, I'm going to skip kind of over these. These don't really. Although any two real numbers can be compared, not all functions are asymptotically comparable. That is, for two functions, f of n and g of n, it may be the case that neither f of n equals to g of n, O of g of n, nor f of n equals to omega of g of n holds. For example, we cannot compare the functions n and n to the power of 1 plus sine n using asymptotic notation. Dang, dog barking. Close the window. Okay, we're almost there. Standard notations and common functions. This section reviews some standard mathematical functions and notations and explores the relationships among them. It also illustrates the use of the asymptotic notations. Monotonicity. A function of f of n is monotonically increasing if m is less than or equal to n, implies f of m, which is less than or equal to f of n. Similarly, it is monotonically decreasing if m is less than or equal to n, if m implies that f of m is greater than equal to f of n. A function f of n is strictly increasing if m is less than n. This stuff doesn't really help us without some examples, honestly. Floors and ceilings. For any real number x, we denote the greatest integer less than or equal to x by x, the ceiling of x, right? Or the floor of x, sorry. Less than or equal to x. And the least integer greater than or equal to x as this, read as the ceiling. The floor function is monotonically increasing in the ceiling function, as is the ceiling function. Floors and ceilings obey the following properties. For any integer n, we have the floor of n is equal to n, which is equal to the ceiling of n. For all real numbers of x, we have x less than 1 is less than the floor of x, which is less than or equal to x, which is less than or equal to the ceiling of x, which is less than x plus 1. We also have this notation, or equivalently this notation, where the negative floor is equal to the negative ceiling, and the negative ceiling is equal to the negative floor. Interesting. For any real number x greater than or equal to 0 and integers a, b greater than 0, we have this. See, they're kind of just throwing some stuff at us here, which honestly doesn't really help us. What's going on here? Modular arithmetic. For any integer a and any positive integer n, the value a and mod n is the remainder or residue of a quotient. Okay, so it's just going over some of like our operators, like floor functions, modular, polynomial. Okay, given a non-negative integer d, a polynomial in n of degree d is a function p of n in the form of p of n equals to I equals to 0 up to, for all values, up to some value of d, whatever, I think, right? The sum up to this, where the constants a0, a1, a through d are coefficients of the polynomial, and a sub d does not equal to 0. A polynomial is asymptotically positive if and only if a sub d is greater than 0. For any asymptotically positive polynomial p of n of degree d, we have p of n equals to theta of n to the power of d. For any real constant a greater than or equal to 0, the function n greater than n to the power of a is monotonically increasing, and for any real constant a less than 0, the function n to the power of a is monotonically decreasing. We say that a function f of n is polynomially bounded if f of n is equal to O of n to the power of k for some constant k. Exponentials. For all real a, which is greater than 0, and m and n, we have the following identities. A to the power of 0 is equal to 1, a to the power of 1 equals, okay, so this is giving some exponential identities, so it's just kind of giving us some basic math properties, right, to help kind of pair with our algorithm analysis, right, some exponential properties here, polynomial properties. For all n, a values, okay, got you, so then some logarithmic properties here, log n equals to log 2 n binary logarithm natural log of n equals to log base e of n, log k of n. So these would be good to kind of reference back into the future, I guess, but it's not really super important for us to kind of read over line by line right now in an audiobook format. Okay. By equation 3.19, right, log base b to a equals log base c to a log base c to that would be, got you. Changing the base of a logarithm from one constant to another changes the value of the logarithm by only a constant factor. Consequently, we often use the notion log n when we don't care about the constant factors, such as in O notation. Computer scientists find 2 to be the most natural base for logarithms because so many algorithms and data structures involve splitting a problem into 2 parts. There's a simple series expansion for the natural log, right? 1 plus x, where the absolute value of x is less than 1. In natural log of 1 plus x is equals to this, right? We also have the following inequalities. We say that a function f of n is polylogarithmically bounded if f of n is equal to big O of log to the power of k times n for some constant k. We can relate the growth of polynomials and polylogarithms by substituting log n for n and 2 to the power of a for a in equation 3.13. This guy here. Okay, factorials. The notion is read as n factorials, defined as for integers, right? This is just going over what factorials are. Functional iteration, we use the notation f, to whatever I denote the function f of n is iteratively and applies I times to initial value of n. Formally, let f of n be a function over the reals. Just kind of getting into some mathematical notation. Iterative logarithm function. We use the log notation log star n reads log star of n to denote the iterated logarithm defined as follows. Because the logarithm of a non-positive number is defined as log I of n is defined as if and only if log. What is this? Bro, we've been taking notes. Please don't come into the stream and start making demands if you haven't been in here the whole time. Not really much to take notes of over here yet. I'll probably go back through and get some notes of some definitions, but I'm not going to take notes over these mathematical equations. They're kind of besides the purpose for our points right now. I mean, we might need them as we analyze and actually, build maybe some algorithms of our own and such, but we can always come back and reference here. Okay, then they also go over Fibonacci numbers as well. Okay, so this says, nice, this section is about iterated logarithm function. Sounds scary then, so let's break it down. What does iterated logarithm mean? Take n, keep applying the logarithm log base 2 to it. Count how many times you need to apply the log before the result drops to 1 or below. It means apply log I times the smallest number of times you must apply log until you get less than or equal to 1. So log star 2 is equal to 1 because log 2 is 1 because it's in one step. Oh, okay, so it's just basically kind of the result of a binary search, like the steps of a binary search. No. Gosh. Is this like counting steps in binary search. The iterated logarithm isn't literally counting steps like binary search. It feels very similar because both involve repeatedly chopping down with logs. Each step in binary search cuts your search space in half. How many times do I need to apply the log until I reach a result is less than or equal to 1? So what's the difference? How many times am I having until I hit 1? How many times do I need to take a log until I hit 1? Interesting. Yeah, then they talk about the Fibonacci here. We define the Fibonacci numbers as this, right? Thus, after the first two, each Fibonacci number is the sum of the two previous ones, yielding the sequence this, right? The sum of the two previous numbers. The Fibonacci numbers are related to the golden ratio and its conjugate, which are the two roots of the equation, this. Cool, so then it gives us into problems. All right, so we'll have to go over these problems on a different time here. I know our notes kind of fell off on the back half here, towards this kind of more mathematical notation stuff, but I'm not going to really take too in-depth of notes. We can always come back to this section of the book to reference these exponentials, polynomials, factorials, all that jazz. But we will go ahead and end it here for today, I believe. Sweet. So we'll come back and take a stab at these problems in another time. We'll let this kind of marinate, and so we'll come back and get some practice with these notations at another time, which will be good to solidify the information here. So this was awesome. This was Chapter 3 of Introduction to Algorithms by Corman and the rest of the MIT staff. CLRS, right? The acronym. Thank you guys so much for being here and joining me. My notes are live on my GitHub if you guys would like to access them. You can also find them in my Discord link down below in the description. But we're going to stop for today, and then we'll come back to at a later time and continue on. But this was Chapter 3, which was a really great chapter on asymptotic notation. I learned about little omega notation, which I haven't learned about before. Which I need to, so I'll go back through and kind of polish up my notes as well for you guys. But if you guys have any resources or feedback, let me know. Shrouded says, just dropping by to say good luck, you've got it. Also, you inspired me to start streaming as well. Nice, dude. That sounds awesome. Good luck with your streams. Later, Tim. I'll see you later, my guy. Thanks so much for coming in. All right, you guys, I will chop up this stream and post the kind of read aloud or audiobook to my channel for you guys to watch and come back and reference. Thanks so much for being here, and I'll see you guys tomorrow on the next one. Bye, guys.